Monday and Wednesday this week, and we'll be talking about instrumentation, data facilities, and cyber infrastructure, satellite comms, etc. on Wednesday. Please keep in mind that this meeting is being recorded and will be available publicly on the UNOLS website. And the usual announcement, everybody should be familiar with Zoom etiquette at this point. Please try to keep your microphones muted when you're not speaking. And if you've got a question, raise your hand and the office will call on you to ask a question. And with that, I'll pass it over to Doug. Thanks.
Thanks, Craig. Good day, everybody. Good to see everybody back. And anybody new is joining us. This is session number 4 in our series. And today it's 4 very important, very interesting areas. So we look forward to hearing the briefers in these. We'll start off with Suzanne Carbot, who's going to talk about R2R, which is this essential, the backbone behind everything that's going on out there when you're doing science. So Suzanne, it's yours.
Great. Thank you so much, Doug. And thanks, everyone. So in the next few minutes, I'll be providing an overview on the data stewardship services for the academic research fleet that are provided through the R2R program. I'll be giving an update on status of services for cruises through 2020 and some highlights on recent developments over the year. R2R is a multi-institutional collaboration between geoinformatics groups at Lamont, Florida State, Scripps, and Woods Hole. We've been in operation since 2009, and we have funding. Our primary funding is through NSF and ONR, with additional funding through from NOAA through the OET program and from the Schmidt Ocean Institute for services for their ships. Next slide, please. So the overall mission of R2R is to support acquisition, documentation, preservation, and enhanced usability of the underway environmental sensor data from cruises conducted with the academic research fleet. The core services include digital curation and preservation for all of these underway routinely operated sensors. We provide the R2R Cruise Catalog, which is a resource for discovering information, metadata about cruises and access to data from cruises. And then we are also providing data documentation, QA services, and level 1, 2 data products for a select subset of the instrumentation to further broaden access. Next slide, please. So this is a summary of the number of cruises registered, managed through R2R going back to 2009. We're showing here the cruises identified according to activity. So the science cruises are in blue, the transits are in pink here. Cruises that were identified by the operators as primarily educational support are in red. And then there's also shakedown cruises, training cruises, and inspection cruises identified. So there's currently 20 active service ships that are being managed. These span the global, regional, and coastal ships. In addition to this, data is now coming through R2R for the Falcor and the Nautilus. Over the time span of R2R, we've had a number of ships go out of service. But those are all within the catalog and available. And we're currently managing about 350 cruises a year at present. Next slide, please. So the focus is on the underway environmental sensor data. There's 32 device types that we currently have documented breaking out from the cruise distributions at the end of each cruise. The left figure shows a histogram of number of data sets for each of these listed data types. And so, of course, the most common ones are the navigation data types, ADCP, CTD, Met Station data, Multibeam, Single Beam, and TSG. The core data types correspond to about roughly a third of the file sets that are being managed. Roughly another third are, more than another third are the navigation related data file sets. And then the rest are the other sensors that are not uniformly distributed across the fleet. Okay, next slide. We're doing automated post-cruise quality assessment as part of our data documentation for the data types listed on the right. So for navigation, multibeam, sub-bottom, gravity, and magnetics, CTD and XBT. The plot is showing the number of cruises each year with the transits, non-science cruises and science cruises indicated. And the lines correspond to the different data types, the number of file sets that have been QA'd for each year. And so you're seeing, you won't be able to read what all the different lines correspond to, but what you're seeing is that we don't have instrumentation, the same instrumentation on all the ships across the fleet. And also that we are seeing some fluctuations from year to year in the number of file sets that are available to QA. And this is due to variations in instrument status and also the suite of cruises that happen each year. But overall, it's fairly uniform across the time period. And this routine quality assessment is possible due to the standardization and routine submission that we've got going. Next slide, please. So the role of the automated quality assessment, there's two main goals. One is to identify suspicious data. The goals are to identify suspicious data, but we have two main categories. One is evaluation of the overall file and metadata integrity so that the files exist, they're the right size, format, etc. And the other set of tests are device-specific tests, which require us to actually open the files, and we're then evaluating them for specific tests. So here's an example for navigation. And the histogram is showing results for all of the tests that are run for navigation for all ships, all years. And so we're seeing the roughly 20% of the expeditions we're flagging as having particularly long gaps that are exceeding the threshold that we've set for yellow or red, and another 20% appear to be incomplete when we compare them to the temporal duration of the cruise that we're getting from the cruise metadata. So this is just an example of the QA results for this data type. Next slide, please. Okay, and then this is a similar plot for Multibeam. We're doing 18 tests for Multibeam, and this again is all ships, all years plotted together. And what we're seeing here is we are flagging about 20% of the file sets with high across-track beam noise, and this is primarily high noise in the outer beams due to, with the modern sonars that we've got deployed on most of the fleet, the modern systems really let you, the full swath width, if you just open it completely, you have very noisy beams in the outer part, and optimal operation is to narrow your swath. So we're seeing we're tracking that. Another test that's showing about 20% yellow, we're seeing fairly high cross-track slopes. A high cross-track slope can be an indicator of a roll bias, but in many cases for the data we've looked at, it's the cruises there's a regional slope through the area that was surveyed. And so we're seeing a mean cross-track slope that reflects the geology. Anyway, this is just to give a flavor for what the QA is providing. Next slide, please. So then we're also producing a suite of data products. Here's the overall status for the 10-year period. Again, as with the QA, there's some variation from year to year, but it's fairly uniform in terms of number of products for particular data types. And we're generating a final R2R navigation product for the majority of cruises, and then evaluation products for these data types: sub-bottom gravity, magnetic, CTD, and XBT, with XBT added in the last year. Also an R2R product is the event log, which I'll be talking more about, and the quality controlled MET and TSG data via SAMOS. Next slide. Okay, so for navigation, this is a summary of navigation status over the years, the number of nav products produced, and the cyan line is showing the total number of cruises. So we're generating a navigation product wherever we have a standalone navigation file to use, and that's in about 85% of the UNOLS cruises. So there's a fewer number of cruises that we can't generate a standalone nav from compared to when R2R began. Next slide. Okay, in terms of support for acquisition, we have a number of services. One is this near real-time quality control of MET and TSG data via SAMOS. There's currently 12 recruited vessels, 20 operator feedback exchanges in the past year, during which we were able to resolve over a dozen MET TSG sensor issues. And this plot on the left is actually, so most of the SAMOS, the data, MET and TSD data coming into SAMOS in since March has been the ships tied up at the dock. But this is a really nice example on the right showing observations recorded through Hurricane Paulette on the Atlantic Explorer, showing the Hurricane Paulette eye and this pressure minimum and abrupt change in winds recorded at the dock. Okay, I'm going to have to speed up. Let's see. Next slide, please. All right, event log. So this is, we are seeing an increase in usage. We had 70 cruises using it last year, so that's roughly a fifth. Next slide. We're also turning a little more towards development of best practices. So we published our best practice document for transmissometer data through the IODE best practice service this year. A few more details on what's in the best practices. Next slide. Okay, then I had new developments for 2020, which I'm going to race through. Next slide. We're now managing Palmer and Gould through R2R. So the full academic suite is now managed through R2R. We've broken out 2019, and the data prior to 2019 will be broken out successively. We hope to get through that in the next 2 years. Next slide. We've published a bunch of, we've written a whole suite of APIs to support machine-to-machine access to the cruise catalog. And those are all posted, available on the website. Next slide. We have an R2R, a new e-log client, which it can be used on your iPhone or iPad. When you use it to document some activity when you're out on deck, once you submit the event, it goes directly into the main e-log. So we think this is going to enhance the usability of the system, given that a lot of what you want to document with the e-log are events happening when you're out on deck. Okay, next slide. Okay, and then this is the last one where we also have initiated a new collaboration with the RDesk group at OSU to explore opportunities for collaboration and information sharing as they are developing their new systems for the regional class vessels. So we held a virtual workshop in May. And some of the outcomes we decided upon some joint working groups to develop best practices for CTD and other underway flow-through sensor systems. We're going to collaborate on use of controlled vocabularies for devices and event logging, so those are consistent. We're going to be providing feedback on Coriolix, their data acquisition system, to optimize the post-cruise data packages for R2R needs at the end. And we're also going to work together on some shoreside data exchange prototypes with a focus on navigation and the MET and real-time MET and TSG data streams. So we're excited about this new endeavor. Okay, and that's last slide. So big shout out to our funders, NSF and ONR, NOAA for all the collaboration, both in terms of funding, but primarily serving as the long-term deep archive for the data coming from the fleet, and Schmidt and UNOLS. Thanks.
Thanks, Suzanne. Very informative. There's so much work you and your team get done behind the scenes, but it's so critical. So thank you. Questions for Suzanne from anybody?
I just wanted to make a comment, Doug. Oh, go ahead. I'm sorry.
Oh, go right ahead.
I just wanted to mention that we are working with MFP and R2R also to see where those two systems can have some synergies as dealing with instrumentation and possibly personnel, and there was a third, organizations. So I hope that we can create some synergies there too, so that we're all have that common vocabulary and making it easier for the whole community and everybody, making it easier for everyone to track their data. So I think that too is a great step forward.
Yep. Thanks, Alice. I have a quick question for you, Suzanne. So this year, where the cruise numbers are down, what is the team working on, focusing on this year?
So because we normally really don't get complete cruise distributions until the end of the year, we've been working on the 2019 ingestion. So it's the coming year which will be lower in terms of the volume of data coming in, lower than a normal year. Yeah. Okay. And so, you know, part of that, we have the Palmer and Gould backlog, or you know, working on that older data set. We're also going to spend some of this additional time on improving documentation of our processes so that we have a more standard and robust suite of documentation workflows.
Great, thanks. I see Mike Prince has a question.
Just a comment. having been there when this first started up and a lot of people sort of wondering what its use was going to be, I really think that the folks at Lamont and Scripps and Woods Hole and everybody that's involved in this project, the Samos people as well, done an excellent job. But I'd like to give a shout out to Jim Hollick for having the bravery to move forward with this in the beginning and really pushing it. I think it's his legacy.
Yeah, yes.
Thanks, Mike. Thanks for putting that in perspective for me. That's good. Very good. Okay, moving on. Next.
Wait a minute.
I think Dennis has a question.
Yeah.
Sorry.
Suzanne, thank you for the talk. Very illuminating. I'm still trying to learn about R2R, so thank you for that. The question I have is, who's the user community? Who are you transferring data back out to for scientific use and that sort of thing? Can you characterize that for me?
Yeah, so all of the core data types that fall within what NOAA handles are going to NOAA. So distribution of the data is through the R2R website, but also through NOAA's archives. So what NOAA has now for example, for the Multibeam data within the NOAA archive, 60% of it is from the academic research fleet. And then we're also, those R2R products that we're generating, as well as like the Multibeam is contributing to these global syntheses that are being produced through JEBCO and CBED 2030. But we really see that the use of fleet data in these global syntheses is an really important way in which we expand the user base. And so it's contributing to the World Ocean Database and various things like that.
Thank you.
Okay, next up is Vicki Farini talking about the Multibeam Advisory Committee, MAC, another very important thing that happens behind the scenes.
Thanks. I'm actually going to tag team this with Paul Johnson, who's my co-lead of the project. I'll give the first few slides and then he'll do a few and I'll wrap up at the end. But basically, we'll just give you an overview. The Multibeam Advisory Committee, also called the MAC, is a collaborative between UNH and Lamont. And we're really focused on making sure that the data acquired with the US academic research fleet that makes its way to the National Archives through R2R is acquired at the best possible quality. Next slide, please. So we were established in 2011 with funding from NSF, and really we're focusing on consistent collection of data through standardized protocols and tools for system assessment, documenting and reporting our findings and making that information publicly available on our website. We provide onboard and remote support for ships for calibration and testing and performance assessment. And we're really trying to broaden the community that shares best practice knowledge and information. And so that's primarily done through our website, but also, of course, through meetings and working with individuals, both in the operator community and also in the science community. The way we've set up the project is to have basically 3 technical teams, although they're really populated by the same humans in most cases, but they're focused on different aspects of the Multibeam lifecycle. So shipboard acceptance team focuses on making sure that the installation was done correctly and that we all have it well documented and clearly preserved for future applications. The quality assessment team does things like calibration and assessment of system performance. Some of those tests are done during the sea acceptance test, but also routinely through the life cycle of the system. And then we have an acoustic noise team, which is really largely led by Tim Gates, to really get in and do even more detailed assessment of the acoustic noise of the vessel and making sure that we understand its effects on the ship. Our website also makes available reports that the same people have generated using the same protocols for other non-UNOLS vessels. So there's NOAA reports there. There's reports there from the Nautilus and also from some foreign vessels. And again, we're really trying to bring together technical resources, cookbooks, tools, et cetera, that can help the community both nationally and globally to acquire better multi-beam data. And we have a help desk also to field questions from individuals as they arise. Next slide, please. So briefly, just sort of an overview of the mapping systems in the US academic research fleet. There are 11 research vessels with mapping systems and 1 Coast Guard icebreaker. The majority of these systems are Kongsberg systems, so that gives us some commonality in approaches and software, of course, and formats as we work through the data and the testing. There are 2 shallower water, I believe, Reson systems, and the RCRVs will be coming online soon with more multi-beams. So this slide is both to show us sort of the breadth of the vessels in the fleet with the multi-beam systems, and also the national synthesis that Suzanne didn't mention, GMRT, the Global Multi-Resolution Topography Synthesis that we curate at Lamont, making use largely of the data from the US academic research fleet, making it available to the public, and then feeding that into global international syntheses like CBED 2030. And again, you know, one of the guiding principles here is you hear often map once, use many times, and really focusing on making every ping count as we go through the global oceans and acquire data. So next slide, and I think Paul will take it from here for a bit.
Yeah, so this is actually one of the slides we got asked to kind of assemble, and it kind of shows where each of the ships are kind of in their life cycle, whether from new to old and whether the system's on a gondola or not. So to the best of our knowledge, we're kind of judging age of the systems by when the array went in. And in some cases, like the Langseth, the transmit and the receive are different ages. We also kind of made notes about what the MAC has done. So, you know, whether we've done a SAT, QAT, whether it was a virtual visit or whether there was people on board. And wherever you see like one of those MAC visits denoted, if you go to our website, you should be able to find a report or multiple reports if there's been more than one visit to the ship. Next slide. So one of the things we set out early on to do was to kind of establish a rigorous testing protocol. So basically, we would know how well the ship performed. So each of the systems on the ship performed, but also the ship itself, and looking at the noise coming from the ship. And this is done, as Vicki said, through different kinds of tests. So there's the initial shipboard acceptance test, and we've done 11 of these, and we're actually currently in the midst of our 12th that we're helping kind of virtually with. So the Ravel's out right now, and we help put together a plan and kind of made a cookbook of all the things that should be done. They're out there running it, kind of looking at the data, and then also sending the data back to us. So far we've already gotten back the EM712 data for their patch test, and also did some preliminary noise assessment on the ship. The next kind of testing was acoustic noise testing, also known as ANT. We've done 9 of these, and as Vicki said, this is generally Tim Gates that does it, but we also do our own testing while we're out doing it as well. So Tim is kind of the specialist in the matter. The quality assurance test, we've actually done 24 of these. Kind of in the last year, they've all been done kind of remotely, virtually, but you know, ideally it would be us on the ship riding, looking at the data, because you do get a better sense of what the data is. And also as part of kind of the system performance testing, we've developed a lot of tools, and I'll actually show a few examples of some of the tools that we've developed. Next slide. So for a typical SAT or QAT, these are kind of the steps that we would go out in. And so this diagram here this is an area off of LA, San Diego, and it kind of shows a typical test that we would do. So before we even go out, and hopefully actually like weeks before we go out, we can do a full review of the geometry and installation of all of the devices on the ship, go through the configurations for the acquisition, make sure everything is set up. Then when we go out to sea, we do a patch test, and this is basically the calibration. So you're determining the biases that haven't been measured between the arrays and the MRU. We then do noise testing, and this is to kind of assess how much noise, different engine lineups we'll put into the water. We'll also look at how the ship performs in different directions relative to the sea state. We then go through and do swath accuracy testing. And this is basically evaluating the accuracy of the system as it passes over what we like a known reference surface. And we've now started to build up enough of these reference surfaces around the different ports so we can actually save a lot of time, just go out and have the ships run over the surfaces. As part of the process of going in and out and transiting around, we collect data that we can use for swath coverage. This is also known as an extinction test. And this is looking at basically the performance, the swath width of the system as a function of depth. And then we also do impedance testing. And the type of impedance testing that we're doing is actually done through using the SIS software to actually go in and interrogate the array. So Kongsberg can actually come in, or you can buy a testing kit that you can actually hook up directly to the arrays, but this is kind of a proxy for that. And like I said, everything we do, we fully document, report, and put it up on our website. And one of the things I was also going to start to point out is we've kind of moved into where when we're working with the ships, as much as we can, we kind of put it up online. So in this case, there's this checklist that basically is a living Google Doc that we can go in and edit. The ships can go in and edit, and it basically keeps a running, tally of like what's been discussed, what needs to be done, and what's coming up. Next slide. And as I mentioned, we also do have a series of tools, and these tools used to be available only through a virtual machine that you could download. Everything was kind of driven through command line, and Kevin Jerem has done a great job of taking these tools and kind of refactoring them into fully standalone Python routines. So there's BIST plotting, so it's built-in self-test plotting where we can go in and plot up the noise data, the impedance data. So in the case at the top, you can see some of the most recent noise tests collected by the Revell while they've been out there. There's swath performance, that's the extinction testing, that's in the bottom right. And like I said, that's not only can you look at kind of your swath width as a function of depth, but you can also look to see when mode changes are happening, what was it, single or dual beam, or other cases. There are swath accuracy that's been just super simple now to use. So a ship can go out and run a line over one of our reference surfaces and they can plot up the data themselves if they want. And all this is available through the website, through our assessment tools, and this will soon also be available through a Git repository. Next slide. And this kind of here is a modified set of perspectives that we kind of came up with during the symposium on ocean mapping protocols, but it kind of does kind of relate to a lot to what we do. And so I'm just going to kind of read this quickly. And really one of the biggest things that we said is that collecting the high quality multi-beam from the beginning, so when it's raw, really does save you time and money, because as other people use it down the road, if you don't have to keep reprocessing and refixing it, it saves a lot of time. We also really do believe that the rigorous performance testing and documentation of that testing catches problems early. So when a ship has a problem, we can go back and look to see how they were doing and say, hey, there's an issue with this. Or we can go on to a ship and say, hey, your array really should be replaced soon because of, the impedance check that we just did. And common testing protocols allows for easy ship to ship and system to system testing. And this has been really useful when we kind of, especially we get a lot of questions from the outside as well saying, hey, how do we compare? And we can say, here's our protocol. You guys can compare your results to ours. The use of common tools has really helped us a lot with system performance assessment, and it allows others to do the same kind of testing we do. Open access to performance reports is critical, and this includes the reports contributed from NOAA and the other folks that we've worked with. And this is kind of we've tried to go down this road a couple times, but we really do feel like the cost of spares is much less than the cost of ship time. And now with the commonality of systems across so many different ships, and with so many different ships, so like NOAA's using them, Coast Guard's using them, like really having a common spares pool at least within the US, would save a lot of time in the long run and money. And the post-cruise quality assessment via R2R and GMRT provides important information about system performance and consistency. And with that, I'll actually hand it back to Vicki.
All right. So just to wrap it up here, a few thoughts about the benefits of this effort to the US research community. Of course, seabed mapping data is an essential ocean observation and has broad interdisciplinary applications. Recognizing just how little of the ocean has been mapped and the investment that has been made in these systems, it's really important that we try to optimize data quality and data flow and also data synthesis and integration. The best practices and the routine system checks that we have implemented are really, I think, improving, and also what R2R is doing, improving what we're doing as a fleet. So the vessels in the fleet are now routinely acquiring data during transits, and that data fills important gaps in coverage, both nationally and internationally. And it's a huge contributor to all sorts of global mapping efforts on various scales. And I think it's also important to recognize the complementary efforts of the MAC, R2R, and GMRT as three funded efforts that exist along the data continuum. When you look at Multibeam data, really focusing on optimizing quality, delivering that data to the public archives, and then synthesizing and integrating that into publicly available syntheses. Next slide, which is my last. Just a few, I think this is my last, a few comments about the presidential memorandum on mapping in the EEZ and sort of casting this in a broader sense. As Suzanne said, very huge, a significant amount of what's at the NOAA archive for Multibeam data is from the US fleet, the UNOLS fleet, roughly 60%, depending on how you look at the numbers. I did a computation based on what's been integrated into the GMRT synthesis, and over 20% of the US EEZ has been mapped by the UNOLS vessels. The plot here shows for individual vessels how much they've mapped within the US EEZ. So it is a significant contributor to mapping our national waters. We did presentations that we coordinated at the recent Standard Ocean Mapping Protocol Symposium, which was, I think, 2 weeks ago, but time is all a blur, really emphasizing the efforts of R2R, MAC, and GMRT and how they feed into this effort. And as Suzanne mentioned, the data synthesis that we are building as a fleet and as a nation are contributing directly to international compilations, including the JEBCO seabed 2030 compilation. I think that's my last slide, but let's just check to be sure. Yep. Okay.
Great, thanks, Vicki and Paul. A lot of great work. I know you, from a personal perspective, I know you guys were a huge help when we brought the Thompson back online, making sure the upgraded system was working optimally. So we know your work is extremely valuable and greatly appreciated. Any questions for Vicki and Paul?
Hey, Paul, this is Dennis Ansel.
Yeah.
Yeah, you talked about the spares pool or pool of spares. Is that something, just trying to catch up, that's something that you're promoting, I guess, because you're saying it'd be less expensive to have it than to not have it. So what are the steps to realize that pool?
It's something that we've talked about with Jim before, so I don't know if he wants to chime in or not. I mean, it's something it was actually included in our original proposal, or was going to be included with our original proposal to fund the MAC, and then things got slightly rejiggered and it wasn't there. And it's something we keep bringing up and saying we should probably do, but I think it's more just a matter of, availability of money. So
I agree. We've talked about this for many years. It wasn't your proposal. I chopped it out. If we don't have money for this, I mean, we should have money for this, but if we spend it on this, what are we not going to spend it on?
Yep.
And the details about where do these spares live? How do we get them to the ship? And most things happened at sea, and how do you get them out there, etc. But hey, I'm all ears. Let somebody propose it to the next panel that we have in February, and we'll evaluate it. If it makes sense, we'll go there.
Thank you.
Thanks, Jim. Rob Spirik's got a question or a comment?
Got a question. What would, say, for example, Ravel look like in the system post not having a gondola, not having a 124? You know, how does the data set change, or how do you differentiate between data that has changed qualitatively because the instrument is more has more beams, or is an upgrade, or is something that is identifiable in the data, rather than this is Ravel in 2018 and this is Ravel in 2020, and you just have to know by the year?
Well, I mean, there's definitely, Ravel now went from just a 122 to now a 124 and a 712. So they brought on kind of that shallow midwater system that operates from about 40 to 100 kilohertz. So we're kind of doing that kind of nearer shore. I'm not saying absolute shallow areas. Like their capability is immensely improved. Like using a 122 for shallower water depths is not a great system. It's the 12 kilohertz system is not meant really to be used in those depths. So that's one thing. The 124 itself over the 122, I think you should have better signal to noise. You have modern electronics. I think one of the big things is you're looking at maybe it's not as like a huge of an upgrade as when they went from a 120 to 122, where you started getting dual pings. But I think it's one of those things you kind of had to do just because with the 122s basically being announced as kind of end of life, limited spare pools. I mean, that's where you kind of get into that need to replace those systems. The Ravel's arrays themselves, they replaced them in 2013, was it? I had it in the chart. I mean, we went out right before then, and they replaced it actually during their when they came in as soon as we got off. But I don't know. You have anything else to add, Vicky, or?
Let me just say that.
Go ahead.
Go ahead, Vicky.
I was just going to say that the risk of the limited spares is real, and it's unfortunate, but that's definitely a factor. But I think generally the better electronics, and we're going to have better data quality for sure.
Yeah,
we'll document it for you as things evolve.
I think that's what Rob's question was. Well, is it really worth it to spend all that money upgrading from a 122 to a 124? And then when are we going to upgrade to a 126? I mean, we do, these upgrades are hugely expensive, and I have the same question. I mean, when can we settle on what we got? At least for a while.
I think you're probably looking at probably at least for the arrays once a decade. I think like most arrays are not going to last more than 10 years. And for some ships, especially ships that, that are working in extreme environments, icebreakers and that kind of stuff, it could actually be significantly less. And I think that, I mean, that's the issue, is that I don't think you need the cutting edge electronics. You don't, like, if you have like what we would put in that midlife and that slide we put up, I don't think you need to be saying, just because the 124 is out, you want to get it at all. And there's actually like, from my personal feelings, I like interacting with the 124s. I actually like the old interfaces with the 122s more. So it's not like everything got better, but I think as those arrays age and spares become unavailable, I think that's when you get forced down that road. But I don't, it's not like you need a new system every 5 years. I think it should be more on the lines of a decade or so. Is that along those lines?
Is there a metric of data quality or instrument quality? Is there a, on a scale of 1 to 10, how does someone see in the data that this instrument is qualitatively better? Is it manifested in something that's measurable?
So for like the case of the Palmer, we actually, NSF went paid to have the top side upgraded. So they were a 120. NSF paid to bring it up to the 122. We went down to do the SAT on it, and we could, so this was actually our first time on the Palmer, and we got on there, and it was like we were instantly like, the swath width is nowhere near where it should be. We were having problems with tracking in the deeper water. So yes, it's like it was instantly recognizable that and that's before we'd even done, impedance checks or anything else. It was like just looking at the data, you could say there's something going on with this system. So we went through, we documented all that. A bunch of stuff happened in the background, and then a new array was put on the ship, not by NSF. So, but by doing that documentation and saying, this is what a normal 122 should look like, this is what you're getting now, you were able to actually go in and get a new array out of that. And so yes, like when systems become compromised, especially at that level, there's a huge degradation. You're not able to map in deeper water, your swath width is compromised, your noise floor is up there, and the data just, it's not great.
And a lot of this we're tracking basically as we process the data for GMRT, we're running the swath extinction plot software. So we have for every cruise that goes in a metric of this, a plot. So we have a catalog of these. So we can actually look at them over time and try to look for changes in swath width as one metric of ongoing performance or possible degradation. And also the BISTs are useful in looking at the health of the system over time.
So I think the following question is that a routine practice, or should it become a routine practice to do that, so we can look for indications of degradation of systems, so then they can project down the road for when, we need to invest in upgrades of systems, or, replacements of, transmit arrays or receiver arrays and things like that.
Yeah, like having BIS results, especially if they're collected outside of the harbor, are great, because you can actually start tracking, when like your system's degraded, what's going on. If there's like a history of BIS, we can start seeing, well, did the noise floor come up, because that can degrade your data, or did something happen to the receiver array? That's one of the easy things that the BIS check. To look at transmit, unfortunately, it's more involved. You have to telnet in, and you got to do all these other things. But even just if that was done like, every 6 months or something like that, or at some intervals that we could see the data, or the ship could. I mean, the tools we've built, you can download them and run them and look at them yourself, but we're perfectly happy to do that and actually maintain that kind of archive of that and look at that information for you.
It might not, though, necessarily give us a binary answer, yes, no, the system needs to be replaced. A lot of the problems can be addressed, right, with some sort of upgrades and maintenance work.
Yeah.
Okay, thanks. That's more for us to think about and talk about, I think. Mike, one last question or comment from you before we move on?
Part of Rob's question, I think, was about on the Ravel, we added not only a 712 and upgraded 124, but we installed a gondola. So how do you differentiate between improvements that the gondola might have provided versus going to a 124?
So that's a pretty easy one. Like, we know with especially some of these ships that bubble washdown was an issue, and that can be seen by both just kind of what Vicky can look at and kind of just doing assessment of kind of the bad beams or pings that don't have good information in them. But we can also look at that, and we would look at that during like the SAT to say, are we seeing bubble sweep down events? That kind of stuff just shows up in the data. Like, it's very easy to detect and see. And when you do have those bubble sweep downs, the data that's collected during them is compromised. So that's a really easy thing to say, hey, does this make a difference from the way the ship used to be?
Well, thank you very much, Vicky and Paul. That was very informative, and thanks for all your great work and all this. Next up is Jules Hummin, who's going to talk about UH-DAS and the ADCP program.
Unmute. Okay, I'm afraid I can't do this in -5 minutes.
That's okay.
All right. So I know this is a very broad audience. Some of you probably have no idea that we exist or what we do, and some of you have heard this talk every year. Okay, ADCP, Acoustic Doppler Current Profiler, sends out a ping at a frequency and uses the Doppler shift of that frequency to measure the motion of the water past the package. In this application, the instrument is mounted on the hull of the ship, and that means that we're measuring the flow of the, well, basically we're measuring the ship going over the water. So the water is moving past at the ship's speed, and then embedded in that is also the flow of the currents beneath the ship. The ADCP listens at different times, a sequence of listening, which gives us bins in the vertical as the echo comes back from different depths. So the picture on the right is a cartoon of actual ocean currents with cartoon arrows drawn on them. Red is to the east and blue is to the west, and the little ship is steaming along on the top, and that's the data set that we're trying to get out of this. Yeah, that's our little logo, raising the profile of shipboard ADCP data. UHDAS is the University of Hawaii Data Acquisition System, and our goals are to have reliable near-time ocean currents at sea for use by scientists and in operations, and to have long-term utility of the original data so that it can be reprocessed with different algorithms if necessary, or new things be discovered. And then the process data should be available if at all possible. Next slide, please. Okay, so what does UHDAS running the ADCP, what does it do? Well, it takes time-stamped ADCP position and attitude data, combines them, transforms them, edits them, averages them, and then produces plots at sea for the science user, NetCDF data set for the science user, plots for operational use. There's a website that gets updated frequently sitting on the computer at sea. So anybody who's got access to that URL on their computer can look at what's happening with the ADCP. So on the right, we have a survey. This is one of the uses. This is a survey on the Walton Smith that's done quarterly. They use shipboard ADCP, which you see here, and lowered ADCP, which is what they're doing on all the little stations crossing the Gulf Stream there. This cruise is important for calibrating a cable that measures transport of the Gulf Stream that runs between Miami and Bahamas. I think it's a very long time series. Next slide. So physical oceanographers, they're all about the ocean currents, so that's what this is, or shear. They may be putting moorings in and they want to have measurements about the currents near when they're putting near the moorings for context. Biological oceanographers might want to know about the backscatter or the currents that are related to the studies they're doing. Generally in operations, if somebody wants to know about the currents below the ship, not just the ship's drift, for instance, CTD wire angle, or when you're towing something. And ROV operations find this to be extremely useful because this gives them a real-time view into the currents that the ROV is going to be encountering. Afterwards, you can take multiple data sets and combine them to compare them with satellite measurements, or there are various time series. The HOT series and the BAT series use Kilomoana and Atlantic Explorer to go to a local site and measure the conditions there monthly-ish. The Oleander goes across between Bermuda and New Jersey, and that's a very long-running time series. The Gould runs across the Drake Passage, and so that's another time series. And recently, the ADCP data, backscatter data, have been increasingly important for biological studies. Next. Thank you. So this would be an example of where somebody needed to pick a sampling location or needed to know the edge of the front. I think this was probably, well, it was the Okeanos Explorer, so it was undoubtedly an ROV dive. You might want to deploy floats or drifters in a current, or you might want to be deploying them one in and one out. You might want to know roughly where it's going to go. And I suspect what they were doing was looking for a place to put the ROV in that didn't have quite such a strong current in roughly this geographic location and depth. So they were steaming to the right. They started at the green dot, they went to the right, and they said, I don't see it quitting anytime soon. And they turned around and came back to the left. And there's a thin green line, which is the ship's speed. So the upper panel is the east-west velocity. So it's going slightly west, and the lower panel is the north-south velocity. It's screaming north at 3 knots. The colors are saturated there. Anyway, so they got to a place where the currents were not quite so strong, and then they stopped and did their ROV dive. Next. This is the Kilomoana 38 kilohertz instrument in the subtropical Eastern Pacific, where there isn't a lot of backscatter, but what there is very visible. And this is either that or this is somebody with a hangover. There's a scattering layer at 9,000 or 900 meters or 1,000 meters, and there's another one at 800 meters. These droopy eyeballs are the, this is the bugs go down. The bugs go down when the sun comes up, and they hang out at various scattering layers, 300 to 500 meters, and then they come up when it's dark again. You're either going to get breakfast or you're trying to avoid being breakfast. Next slide. So what does UHDAS do? It starts by acquiring the data. As Paul and Vicky were saying, you have to start by doing that well, because if you mess it up at the beginning, it takes a huge amount of time to get something useful out of it, and that thing doesn't have as good a quality as it should have. So we want it to be, we want the acquisition to be reliable and robust. We have duplicate feeds. We can handle multiple ADCPs. We like multiple GPSs because we want to have a failover in post-processing, and we need an accurate heading. As I said, the ship is moving at about 10 knots, and what we're trying to measure is a couple of tenths. So we need the heading to be accurate to within better than 0.1 degree. 0.02 is probably about a reasonable target. And that is probably by far our biggest continuing headache. We monitor it. We need to make it keep working well. It's sort of like trying to get an elephant to go down a path. That's fine if it's going down the path, but if it starts to move off the path, then you need to gently tell it to get back on the path. It's something that moves slowly and inexorably, and so the data, once it's coming in well, then that's fine. And if there's a little problem, then we need to contact the people on the ship and figure out what the problem is and try to fix it. Processing, the at-sea processing is automated, and so it provides a near science ready product for people to use at sea. You can certainly start doing your calculations with that data set. We would never say that it should be released as processed data for anybody to use and throw into a model, because there could be a problem. The elephant might have walked off the path, or maybe the GPS you're using has dropouts and you don't want to break the data set up, but it's okay to reprocess it afterwards using another GPS. We want to balance the real-time output being useful with post-cruise recovery. We have access to data and figures. That blue thing, if you're actually on the PDF, you could click on it and take it to the website. And we have portable code, meaning it runs under Windows in a virtual machine, or natively, or that same virtual machine on Mac or Linux. And the documentation can go with you, or anyway, I'll show you those in the next slides. And I'm seeing a chat here and it's in the way of my seeing the screens. We want to improve QA, accessibility, visibility, understanding of the ADCP data and the ADCP ecosystem. And we absolutely rely on R2R and NCEI for the conduit and archiving. Next slide. Okay, don't try to digest all the pictures. Just have the overview that in the left, we have diagnostic plots, which help the person at sea see whether there's a problem with various things. In the middle are the plots you might use for science. Did we go through the front yet? Have we reached the latitude of such and such yet? Or at least what do the currents look like? The ones on the right are different kinds of plots that are more operational. The one at the top with the little arrow heading up at 10 o'clock, that's what we call the bridge plot. So people on the bridge can see these as well. If they have access to the website, they can see any of these plots. If you click on the link in the talk, you can go to an example website, but I can't show you that here because I'm not driving. Next slide. Again, a cartoon. This is what the documentation looks like. The first page of the documentation, there's our raising the profile little icon over there in the corner. It is a self-contained website. So if you don't go, and most of it doesn't point outside. So if you have, if you want to know about installation of our software or processing or operations at sea, you can download a zip file or a tarball. You can go to the website that's on the ship, or you can put it on your computer. We have it on the web. It's yeah, all over the place. Next slide. Okay, so the UHDAS system replaces the commercial system, which is a Windows program that would have come with the instrument when you bought it. These are RDI instruments, so that's called VMDAS. And we have all this other value added. So it basically does, VMDAS does the acquisition, the time stamping and the combining and the averaging, but we have a whole lot more checkboxes that we do than they do. There are 17, why do I have 17 here? That doesn't seem right. Well, I'm not going to count them. Anyway, we're on all the UNOLS ships except for the ones that haven't been built yet, or we're not actually on the Rachel Carson yet. It's on the list. There are, 17 because there's 3 polar ships. They're a different category. And 11 NOAA ships and 6 other research ships, Falkor, Point Sur, Investigator, which is at CSIRO, Christine Bonnevie, which is in Norway, and the Discovery and the James Cook are the National Oceanographic Center in England, and 2 volunteer observing ships, which are sailing, Oleander and Norona. And then there used to be 2 more, the Adventure of the Seas and the Flora were Royal Caribbean, but since the cruise liner system tanked during COVID, we got the plug pulled on that one. Next slide. Okay, well, who are we? So this all started with Eric Fearing, who's a physical oceanography professor at the University of Hawaii, who was very interested in ocean currents, measurements of ocean currents, and trying to get something useful out of this new instrument called an ADCP. That was in the late 80s on the Moana wave. He wrote tools to analyze the data, got NSF funding to create a software system to process it, CODIS, which is still running. It has moved from running on a DOS machine all the way up to now. We keep pushing it along and upgrading it and altering it. And so it's grandfather's axe, but it's had about 2 new handles and 1 new blade, but it's still grandfather's axe. The software has been publicly accessible since the beginning. And these days it's a mercurial repository, which you can pull down, or collection. And the documentation, like I said, is maintained. I got my PhD with Tom Rosby at the University of Rhode Island and did not want to be a grant writing research academician. And Eric had a job that offered me all the fun and none of that. And so I came to work for him in the mid 90s, and in the late 90s, turned my focus fully to shipboard ADCP. And that was essentially the beginning of the development of UHDAS. We put it on the Kila Moana. That was the big goal. We put it on the Kila Moana when it came out of birth. And then Sandy Shore reached out to us and wanted to see us become more official and start putting it on the UNOLS ships. And in 2015, we got a grant from NOAA to put it on the fishery ships. For that, we needed another person. We hired Toby Martin. He's been a fabulous success and has added a great deal of depth to the group. So he had previously worked with the Wacoma and Oceanus at OSU. It quickly became obvious that we were not sustainable as Eric and Jules and Toby if we wanted to continue on into the future. And apparently we are successful and we do want to continue on into the future. So we hired 2 more people, and they were both, the economy was good and we didn't have any qualified US people applying. They both came in on H-1B visas, and then various things have happened over the last few years, making it extremely difficult for people with H-1B visas to stay or to feel comfortable. And basically they said, it's too hard to be here, we're leaving. So they both gave us notice. One gave us 6 months notice, one gave us a year. Ugo and Thomas really made the whole thing into a team. We were very sorry to see them leave, but we were very lucky to hire Joseph Gum, who had been in Hawaii before as part of the HOT program, and then spent 10 years at Scripps with ODF, and now he's back. And so we are a group of 3. Eric retired in June, but he's still very much involved. I am the leader, and we are probably going to be hiring another person at some point soon. Well, starting the process. Hiring never happens soon. Next slide. Okay, what do we do? On a day-to-day basis, we get an email from each of the ships, the primary computer that would be doing the logging. It is an automated email with a whole bunch of diagnostic information and some figures, a few figures, a snippet of data. We always try to keep our bandwidth use so low that 1 year of data that we get from the ship by this mechanism is less than one scientist would use on one cruise. So I like to have people say, oh yeah, you're not a problem. We have a ticketing system that Thomas wrote that is very tailored to our needs, and it raises flags by automatically reading the email. We also read it and we look at all the pictures. We communicate with the techs on the ships if we need to for some reason. This blue thing here is the monitoring dashboard, publicly accessible, which I'll show you next. We answer questions from scientists and technicians. We provide advice, if we can, about settings, installations, instrumentation. We are always trying to improve the diagnostics and the figures. It takes more work to improve the processing algorithms, but there's still work that can be done there. Underlying software is a moving target because everybody else out there is trying to improve things. And so every now and then the rug moves out from underneath you. So those primarily include Python moving along, Matplotlib, which is our plotting package moving along, and the Linux operating system distribution that we use. And every now and then RDI comes up with another instrument, and they have just done so. And so the Blue Heron has purchased a Sentinel V, which is the replacement for the Workhorse, and they shipped it to me. So it's in my office waiting for me to start trying to communicate it with UHDAS, which we have to be able to do, and read its binary data and understand its command structure and stuff. That one should be straightforward. The Pinnacle 45 is different. It's another phased array, not replacing, but they built it as a mooring instrument, and now it's the Ronco Pinnacle 45. It slices, it dices, and it makes you coffee. And so we really, really don't believe that. We really, really want to evaluate it and find out what it actually does. So they're loaning one to the Sally Ride, who is going to put it on the pipe stem and put a fairing on a flange that they're going to build. And we're hoping that all of this works out and that we can get a week of data in early December. But that means we need to spend 2 weeks in the middle of November learning how to talk to it. So I hope all that works. Next slide, please. Okay, on the left, we have the dashboard. So if you click the link, you get to the dashboard. On the very left are the names of the ships, and then blue links to figures that came back from the ships. It's easier to go to the website. This is just to treat it like a cartoon. But it has a status of whether when the last email came in, or when which cruise is presently logging or not logging. The DIR there and on the right-hand two blue columns, the DIR is the diagnostics directory. It's got lots of little snippets of commands about the operating system. And then the actual text of the email is the link there. The top block is the UNOLS ships. And we submit our request for funding as a supplement through the Kilomoana's ship operations. So I have no idea how much of our funding comes from ONR versus NSF. I think it's probably mostly NSF. But we basically cover about 2 people through that amount of work, one senior and one less senior. And then we have the NOAA block, which is next, and that's essentially takes a full-time person. All the little pieces down below, everybody who's got a ship got an icon, so there's a bunch of little brands down there. We have so the Schmidt is helping us with the Falcor, and they are actually helping us even more than that, because we're helping them by putting UHDAS on the ship, and they are helping us by paying us to process their data, which means that we have a far better look at the quality of the Falcor data than we do any other ship, because we aren't typically actually getting deep dives into the data after it's been processed or doing the post-processing, but we do that when we can. The Norwegian ship, the English ships, the Oleander. Next slide. So recap of 2020, big experiment for us, which we don't have any choice about, is to run UHDAS on a virtual computer. They're using a cluster, and so there is no physical computer. There's no serial port. So that's so far things are, and in terms of pass fail, it's pass. And we have a lot more understanding to learning to do about whether there are subtle problems or not. But they're at sea, as Paul said. In March, there was no travel. I came back from updating putting a virtual machine on the Sproul, and a meeting in San Diego, and I came back and that was it. I've been sitting in this chair ever since. And so we were normally, to do operating system updates, we have to go in person, and we visit the ship, and we talk to the people and create food stories and update things. Somebody's mic is on. Somebody's making coffee. But we did have an opportunity here because the ships were in port for a long period of time. They had good power and internet. Sometimes they had technician support there, and they had a reliable schedule. And so we actually got pretty much all of the updates or upgrades that we might have expected to do during 2020 done between April and July. People shipped us disks. I mean, Toby built disks for the NOAA ships because they're all using the same computer. So he could build just a hard drive and send it out. People with Linux technical support and a good internet connection, we worked remotely with them to install, and they never shipped the computer. We just did it completely remotely. And then there were a bunch that where they actually just FedExed the computer. The Langseth just pulled in. They're going to FedEx us a computer. They could do the technical support, except they're all leaving the ship right now. So we ended up upgrading 21 computers, complete with the operating system and all the configurations and everything else. 21 computers or UHDAS systems on 16 ships. And additionally, we had increased our monitoring capability of the GPSs that we're logging. And so that meant we had an update in the UHDAS code base. So we went out remotely to 20 ships and upgraded that part of 27 computers. Next slide, please. Coming up in just coming up, we have the Sentinel-V on loan from the Blue Heron. We've got the Pinnacle coming up in December with the Sally Ride. It takes quite a bit of time to actually make the install process work on the next operating system. And so with the number of ships out being decreased, that actually allows us to have more time to do these sorts of things. So that's the next big push, is to start working on, continue working on the install process for the next operating system. We will hire one more person starting soon, don't know when. That's the last slide. And we're running late. If somebody has a burning question, you can ask me now, or you can put it in the chat here, and I can, I don't know, Alice, you tell me what to do.
Thanks very much, Jules. I think that's a great suggestion. If anybody has any questions, they can ask in the chat box. Thanks so much for the great work you and your team do, and I'm glad to see you able to capitalize the time when you couldn't travel this year. We're used to seeing you everywhere, so it's kind of odd to see you in one place, but thanks for just being on top of everything. And for all of you who didn't know, Jules, along with Lee Elliott and Brandy, are doing a phenomenal job getting ready for RV Tech as well. So thanks for all those efforts as well, and in all your free time. With that, I think we should move on in the interest of time. We've been talking about systems that are in place or activities that have been going on for a while, but now we're going to talk about the future a little bit. Chris Ramsos from Oregon State is going to talk about Coriolix and what they're developing there at Oregon State. Chris, with that, please take it away.
All right. Thank you, Doug. Thank you, everybody. Yeah, let's just get right to it. Nope, go ahead. Next slide. I'm Chris Ramsos from the RCRV program, and I know we're a little bit late, so I'll go as fast as I can. So I put this presentation together for you today to give you some background on what the RCRV project is doing specifically to make sure that the information, the data that the RCRVs collect can make it be made available in real time, both locally on the ship and remotely on the shore side. So we're going to go through, we're going to take a look at the suite of instruments and Coriolix, our software implementation, in a minute. But what I hope you take away from this presentation is that the project is definitely delivering a robust research platform with a comprehensive suite of resident equipment, resident instruments. We are trying to be as forward-looking as we can, particularly in this area of remote participation and also, I should say, shoreside support. UNOLS gave me a beautiful setup for this follow-up presentation, because I think a lot of what we see in that model that UHDES provides are opportunities for us in data presence. I also want to say, I want you to understand that we are taking every opportunity to engage with our academic partners, our support partners, be that R2R. Suzanne mentioned an engagement in her presentation, SAMOS, Multibeam Advisory Committee, High Seas Net, UHDES, so that we can really ensure that these vessels, when they come offline, go through their transition year as efficiently as possible and things are lined up. We are keeping close touch with our regional partners. These vessels are going to be across, on our 3 coastlines. We've got regional research infrastructure on some of those coastlines. So we've got some collaborations with OOI and moving data back and forth with them. We're also keeping tabs on things like the NOAA PACE mission and some activities of a NASA PACE mission and some NOAA activities. And finally, I want you to understand that we try our best to learn from what we're doing and continuously improve. So we have deployments of our data presence system on our research vessels that are at our future operators. So we're on Oceanus, we're on Point Sur, we're on Endeavor right now. They're doing different things on each boat, but using that to get feedback from our users and build comfort, build experience, work through problems. Next slide, please. Okay, Daryl Swenson will give you a full project briefing, I think, in about a week or so. So I'm not going to get into the high-level RCRV details. I think most everybody probably has a good high-level view of the project. We're in the construction phase right now, and I think that's what I want you to understand. So there are 3 vessels under construction at Gulf Island in Louisiana. Next slide, please. Okay, who are we? Well, we call ourselves the RDESC, the Regional Class Research Vessel Data Presence and Engineering Support Center. We've been incorporated into all the phases of the project. So there are more of us than these three faces you see here, but these are the 3 people that are responsible for Coriolix and for data presence, under their job description. Katie joined the project very early in proposal phase and has worked through specifying the sensor suite and doing the procurements for that. And she brings a really solid bio-optical instrumentation background to the project. We're very lucky to have her. Same thing with Jasmine. Jasmine's been at OSU longer than I have. We both joined the project in 2015, but also has bio-optics, physical oceanography background, some serious data management chops, and is an excellent web developer and graphic artist. So, and then I get the fun job to lead the project. My background's in marine fisheries and GIS, probably the least exciting of the backgrounds. Next slide, please. So it's our primary responsibility to develop and deliver the data presence capabilities for the RCRV. And I've said data presence probably about 10 times without defining it. And I imagine you can picture what data presence is. If you are familiar with telepresence, we really think of data presence as existing in that space between not sending in information home and sending, having a conversation with audio-visually home. Data presence is supplying that quantitative information from the vessel to remote participants. And that's, in a nutshell. I think, why do we do this? Well, we do this because we all understand that at sea, it's always been a limited resource endeavor, right? Berthing, time you have at sea. So our job was to look at those problems and think, how can we organize, how can we integrate some, admittedly, some pre-existing ideas. We definitely didn't invent this idea, but we looked at it. What can we provide in the planning phase? What can we provide for people on the vessel and on shore to stay aware of what's happening? How can we streamline scientific workflows with a technology like this? How can we connect you to your outreach pipeline? So those, I'm going to go through some examples of that shortly here. Next slide, please. So I really think of the sensor suite as I even wrote myself some notes so I didn't mess it up. We consider this resident sensor suite to be really a foundation for data presence, meaning that we selected the instruments or the sensors for this suite to provide robust and measurements that apply to the research questions of the day. It had a lot of oversight on this. What I want to draw your attention to is these are the groupings by system: flow through, profiling, CTD, met and atmospheric, acoustic, and other. And the light colored items are instruments that are common in the fleet, and the darker blue color change, contrast rather, are new instruments that you'll see on the RCRV and you don't typically see in the US research fleet. Next slide. One more foundational technology. I should also follow up on that last slide by saying there's two pieces here, right? We want to unlock the information and make it available to remote participants. And the reason that sensor suite is foundational is because we really also are very concerned that we're supplying very useful information. I wanted to just quickly stop on the SATCOM for a moment. This is a specific design for RCRV. Kevin at HiSeasNet likes to call it the RCRV reference specification, I think was his term. And what I want to point out is that you have a primary and secondary system on RCRVs. You have a 1.5 meter KU, KA swappable dual antenna system on the pilot house top there that will provide an unobstructed view of the sky. So this gives us our 99, what we're shooting for in the 99.9% uptime. So no mass blockage. The secondary system is a 1 meter global express system. There are 2 green circles there. It's really just a 1 antenna system, but that's a back channel, the other one. But having 2 systems that you can run simultaneously provides a great deal of flexibility in configuration. And we looked at and worked with our partners, particularly the East Coast Oceanographic Consortium and HiSeasNet, to really make sure we were well positioned for bandwidth expansions for telepresence and things like that. So next slide, please. That kind of wraps up the supporting technology. I always like to make the point that Coriolix, which is our software implementation for data presence, isn't necessarily a data acquisition system. So this is my attempt at a graphic that shows the difference between what data acquisition is concerned with and kind of what it does for you, namely capturing sensor observations that have across the transmission network and are stored. Well, Coriolix is really what's right of that, and is concerned with how do we manage our users, how do we provide our users on the shipboard side and the shore side a common environment, what types of services are we going to put together for these users. So just a little bit of orientation One more, Alice, there's an animation here, I believe. So I mentioned at the top of the presentation that the overarching objective is to mitigate these resource limits. One more click, Alice. And I mentioned how we were going to do that. So I'm going to give you some examples of our planning tools, our situational awareness, and data workflows. I don't have much time to go in any deeper than that. But I will provide a link at the end of the presentation so that you can check out our demonstration site. And I should probably also put in a plug at the, we'll have another follow-up presentation in our VTech. Okay, next slide. So I wanted to start here. So what we see here is just, I've taken a screen snapshot, logged into our Oceanus Coriolix website. I've logged in, so I've authenticated, I've gone to our cruise configuration page, and what I'm trying to show or explain is that there's an integration that we've built with an upstream tool, UNOLS Cruise Planner, that as its name would suggest, is used to gather all the information that is going to help you plan a cruise with an operator and their technician support. We use that to help us onboard the configuration for Coriolix. So you might learn things in your pre-cruise planning about which sensors you want, how you want them configured. It allows us to pre-populate all the people that'll be on the boat. So that, I just wanted to start at the very beginning that's a planning integration. It really helps us reduce repetitive, data entry, lowers the chance that you're going to make a mistake. And in other slides, we'll show a little bit more about maybe geospatial planning and things like that. Next slide. I talked about situational awareness, and we always kind of like to start with this slide. It's another page in the Coriolix web user interface. And it's just a simple status screen. This is, again, Oceanus, but it tells us really quickly, you can look at this from shore and know really quickly that you've got a problem in 3 instruments, in this case, they're not on. There's a banner right at the very top that's telling you what conditional type alerts have been fired recently. If you've subscribed to those alerts, you'll be getting notifications on your Slack channel or in your email that there are problems happening. But this is something that you see on every ship that you go on. It might be on a scoreboard in the lab. It might be in the, in the high bay. It might be in the mess. The difference here is if you click one more time, Alice, thanks. I think I had an animation, is you can take it with you on your phone. So if you're or on your laptop, so you're not tied to that physical display in the lab. It's a mobile, it's a distributed interface. Next slide, please. More about situational awareness. We tried to build on what Steve Roberts had developed at Alaska. Admittedly, a more simplified version of what you all know as map server, but the idea being to provide some geospatial context without providing and burdening the technicians with full-blown GIS. But so we built in a web mapping tool into Coriolix, and I think the key thing to know here, the approach to something like this is we're providing levels to kind of those foundational data sets, such as Vicki was talking about, the global multi-res bathymetry topo. I've covered it up with a satellite image here, but the land that you see on Western Oregon there is actually coming from that GMRT. So we're looking at other curated data products from that type of a collection to preload. So you have a local cache of information on the boat and on shore. We're building subscriptions to remotely sensed data. So I've got an overlay of sea surface, chlorophyll concentration. And that's a subscription. We use a NOAA product called an ERDAP server to subscribe to a data provider, a terrestrial data provider. And once a day, that ERDAP server that's on the boat downloads that product. And now that product becomes available to your shipboard science party from a local source. And we can identify, and through pre-cruise planning processes, we can identify what remote data sets we might want to subscribe to for a future cruise. We do things like waypoint and route planning in here. You can toggle to a screen, lay down a track, save it, give it a name, I haven't implemented yet, but convert the format into standard interchange formats like GPX or something like that. So that's optimizations to kind of make bridge to operations a little smoother. Next slide, please. I could talk more about situational awareness, and we can look at 2D plots and things like that, but I always skip over some of this stuff, and I think it's important. When we're talking about building tools for science, the data services, I think, are a very important component of Coriolix. So you can go to Coriolix and learn about how the data is stored. So a lot of documentation. We've provided data access for humans, through a GUI here. And then which makes it very easy to, on the fly, go down and grab something that you're interested in. And then if you find yourself repeatedly going to that and downloading it, and maybe you want to do something with the script, the data services that are powered on the back end by ERDAP again will allow you to, say you have a workflow that you've developed in Jupyter or something like that, you bring that on the ship and wire in the data source and start to do things more automated, more intentioned, I guess. So I did want to reveal that also, some of the less flashy but very important part of Coriolix. Next slide, please. Okay, now we're starting to get into kind of what I really wanted to talk about was maintenance and management. I think that Coriolix really provides an opportunity to up our maintenance and management game, I guess, for lack of a better way to say it. And what I mean by that is to extend that so that shoreside people can really take part and assist, right? So here I've given you a couple screens, right? It's difficult to, without going through a live demonstration, I've taken some snapshots, but what I'm showing you is there's a wealth of information, a wealth of metadata that we save about the instrument, and we start that collection of information from our procurement. So we're maintaining a history for all of our instruments, and that we can synchronize that information to all the ships. So that really facilitates sharing equipment a lot easier. We can let a shoreside technician go in and set up a configuration for an instrument. And one of the recent integration projects we finished was, I showed you a slide earlier that showed OpenRVDAS as a data acquisition system upstream of Coriolix. A recently completed project allows us to use Coriolix, the information that the technician maintains in Coriolix, to configure how OpenRVDAS works. So we realized, rather than maintaining two kind of siloed systems, provide for the configuration of the acquisition side through this archive of information, or this managed piece of information. So I keep coming back to this idea of, I think there's a lot of things that Coriolix provides right out of the box for the at-sea crew science parties, but there's more yet to realize, I think, from a shoreside support side of the house, but we're not there yet. Next slide, please. So at the top, I said, okay, we're working to consistent outcomes. What does that mean? I think, I wanted you to know that we're looking for what's happening out in the future in our transition phase, and trying to make sure we get everything lined up. And what are some actions that speak to that? Well, I think I'll just pick out a couple from this list. I think one of the good things that we did is in 2015 is we spent about 3 months in the summer going out and talking to people in the fleet, visiting them, sitting down with them, asking them questions. And that really guided our development process. I would say right now what is happening that's very exciting is what Suzanne was talking about in her first meeting. There's a really great engagement going on right now with R2R, and that's because of the people involved. I think R2R has really been great in reaching out to us, working, generating ideas. Katie and Jazz are very on top of working with them. So there's some things in the ocean best practices space that are going on with those guys. They have really expressed interest in what they can learn by monitoring data feeds from ships that solves tiny little problems for them, like just verifying that the cruise is actually on the schedule that was published, little things like that. What I'm trying to say is there's bullet points, and then there's added value from that engagement. And then I would say in the immediate future, what really is exciting to me goes back to what Vicki was talking about, maybe not so much in this presentation, but on the standard ocean mapping call, and talking about the GMRT and the global efforts to kind of come up with the synthesized products. What's really exciting is that some of the workflow, I think, from the GMRT is something that we can maybe implement on the vessel. So there's more on the horizon. There's stuff yet to do, I guess, and I'm very excited about the opportunity to do that. I think I have one more slide, and hopefully I gained some time. Continuous improvement. I mentioned we're already, we're actively engaged with each tech team on all three of these vessels. You should see our email chains. And we're trying new stuff with each team. We've been on Oceanus the longest. We really worked through a lot of our connectivity problems, our different modes of replicating the information to shore. But it's been great to work with those teams. I'll leave it at that. I think there's other things that I wasn't able to talk about. That we're taking opportunities as they arise. The literature showed that maybe diaphragm pumps were a better way to go than impeller pumps in our flow-through system. We made that change. Katie designed and built a filtration system that will allow our scientists to run filtered seawater to get background signal, monitor for biofouling. The sensor manifold is a very configurable design. So all these pieces fit together is what I'm trying to say. And again, get back to that opportunity to leverage a system like that for shoreside support. So the picture is what kind of, we hope is what Coriolix realizes for us, either, students in an outreach event like this, or maybe that is your shoreside technicians working on a problem together. I think that's where the real exciting stuff is. One more slide, Alice, and I am finished. I think when you try to do an acknowledgement slide that includes everybody, you're doomed to forget somebody, and I apologize if I forgot you, but it's been a very broad effort, and we try our best to not be working in a vacuum. If you click one more time, I'll give you the link to our demonstration site. Go to that demo link. You can create an account if you'd like. You can take the QR code, and now I'll wrap it up and take any questions. Thank you.
Thanks, Chris. I feel bad because I feel like you were squeezed in and trying to rush to do it. You can talk, I know, for hours about this.
I can, yeah. I never met a stranger.
Yeah, that's a good thing, though. Incredible work by your team. It's great to see what the future can look like. I'm glad you get to think about that and make it happen, a reality for all of us. Real quickly, we'll see if we've got a question or two to ask you. We know that people can contact you easily if they need to, but let's see if anybody's got any questions right now to pass on to you. And are you also doing a talk for RV Tech coming up?
I am. And
okay.
It takes about an hour or more to lead somebody through Coriolix. And I didn't want to do that to you. So if there's interest, reach out. We'll make the time to sit down with people.
No, there's no doubt you guys have been great about that. As I've gotten to see through the SOC. So thanks for all your efforts, and thanks to the rest in the project by NSF with these class of ships to really push the envelope forward for what is possible in the future. So, which I think will lay the foundation for the rest of the fleet. We need to work with you on MFP, so we'll be talking to you some more about that.
Yeah.
I also just wanted to say that the presentation from our VTech will also be on YouTube as well.
Excellent. With that, I think I don't see any other questions for you, Chris. Thanks for doing a great job. As I know you felt crunched the whole time, but thanks for doing that.
No problem.
With that, I think we're done for today. Any last comments from Craig? Thoughts?
No, great set of talks. Lots of information. Thank you.
So we're back at this Wednesday, same time. We're going to be talking about cyber infrastructure, cybersecurity, and satellite communications, which goes hand in hand with what we talked about today, and the constant presence and monitoring of systems, communicating with data back and forth to shore. So we continue on these very important topics that allow science to happen at sea, especially when we ever do science parties these days. So it all ties together. So thanks everybody for your time today, and we look forward to seeing you on Wednesday.
Thanks, everybody.
Thank you.